Hello everyone, and welcome to the show. This is episode 3, Numens and Correspondences, but this is of q-adic analysis and the Collatz Conjecture, a video series that I'm making to accompany my 2022 PhD dissertation of the same name. In episode 1, we saw some of the bizarre new phenomena that I discovered in my research. In episode 2, we got an introduction to my research as a whole, and here in episode 3, we will finally dive into the meat of things. I have 2 goals in mind for this episode. Constructing the numen of the shortened qx+1 map, TQ, and proving the correspondence principle, the CP, both the full version for periodic points and the partial version for divergent points. We'll then finish up with a discussion of various implications of this work, as well as possible avenues for future exploration. Basically, this video will cover most of the content of the first 2 posts of my 4-part blog posts, series of blog posts on my website. So, since we are finally going to be doing some proofs, it's worth mentioning the prerequisites for this video. Yes, there are prerequisites. And those are an introductory undergraduate course in real analysis, and also it helps if you know what a p-adic number is, though that's not strictly necessary. And that's it. Those are all of the prerequisites. You don't even need to know calculus. Yes, really. The road to the correspondence principle is entirely elementary. Before we begin, though, it's worth going over some basic ideas from the theory of dynamical systems. So, given a set X, and a map from X to X, I write T circle K to denote the composition of K copies of T with itself. By definition, T to the circle 0 denotes the identity map. In a dynamical systems context, traditionally one would not write the circle and just write T to the K to denote the kth iterative T. However, 1, I am very pedantic. I cannot emphasize that enough. And 2, we're going to be doing a lot more than just dynamical systems, so it's preferable to work with the completely unambiguous T circle K notation. So now the definitions. These generalize to dynamical systems on discrete spaces, but here we're only going to be concerned about stuff on the integers. So let X be an integer and let T be a self-map of the integers. We say X is a periodic point of T if applying T some finite number of times to X will send us back to X. For the shortened qx+1 map, the shortened 3x+1 map, the periodic points that we know of on the positive integers are 1 and 2. A pre-periodic point of T, meanwhile, is an X which is sent to a periodic point. So this means that every periodic point is pre-periodic, but not every pre-periodic point is a periodic. And so we say X is strictly pre-periodic if X is pre-periodic but not itself periodic. So for the shortened 3x+1 map, 4 is strictly pre-periodic because it gets sent to the periodic point 2. A divergent point of T is when the iterates of X under T diverge to infinity or in absolute value. This is the ordinary real absolute value, and the divergence occurs in the topology of the reals. Next, we have the sets of import. So, given our X, we define its forward orbit, also known as its trajectory under T, as its sequence of iterates. By a divergent trajectory of T, I mean the forward orbit of a divergent point of T, assuming such a point exists. A cycle of T, next, is a set big omega, which is the forward orbit of a periodic point of T. Note that the restriction of T to big omega is a bijection of big omega, and if we enumerate the elements of big omega as in their chronological order, meaning we pick some element x0 and then label its iterate x1 and that x1's iterate x2, etc., we'll eventually reach xn, and xn will be equal to x0, where Yes, and in that case, the action of T on that enumeration will be a cyclic permutation. So from a group theoretic perspective, the action of T on a cycle is transitive. Next, we have the definitions of orbit classes. So an orbit class of T is a non-empty set V whose preimage under T is the same as what we started with. T inverse of V equals V. So letting V be an orbit class, I say V is irreducible if it cannot be written as the union of two non-empty disjoint orbit classes of T. And obviously, if V can be written as the union of two non-empty disjoint orbit classes of T, I say V is reducible. A periodic orbit class of T is then an irreducible orbit class which contains a cycle, and a divergent orbit class of T is an irreducible orbit class which contains a divergent trajectory. Finally, a given x0, a backwards orbit of x0, is a sequence of preimages of x0. So x1 gets sent to x0, x2 gets sent to x1, gets sent to x0, and so on and so forth. If T is not injective, in general, you're going to have lots and lots of different backward orbits. In particular, for the shortened qx plus 1 map, the backwards orbits are most of the time going to be infinitely many of them. Although there's one exception: if x0 is a multiple of q, its preimage is just the only possible backwards orbit we can have will be twice itself. And anyway, given any x0, we can always get a backwards orbit for the shortened qx plus 1 map by just considering 2 to the n times x0. Now, classically, pun intended, the orbit classes of T arise as the equivalence classes of T's domain under a relation which we described below. So let T be any map on Z. Then the collection of irreducible orbit classes of T partitions Z into at most countably infinitely many pairwise disjoint sets. These sets are the equivalence classes of Z under the following relation, which is sometimes called merging. We say that X twiddles Y if and only if X and Y are eventually iterated to the same point. Finally, we have the following fundamental result, which classifies the dynamics of dynamical systems on Z. For any self-map of Z, every irreducible orbit class of T is either periodic or divergent, meaning that for every integer x, it is either going to be a divergent point, meaning it gets sent to infinity, or a pre-periodic point, meaning it gets eventually iterated to a periodic point. The proof of this is really straightforward. It's a good exercise. The basic idea is to use the pigeonhole principle. If x is not a divergent point, then its iterates are going to lie in a bounded interval centered at 0. And since there's only finitely many integers in that interval, the pigeonhole principle forces x's trajectory, which contains infinitely many points, to hit some point in this interval twice, which means that it's a cycle. And this is the result is crucial because it's going to give us the non-constructive proof of the correspondence principle for divergent points. And our last bit of preparation is one of the most important things you can know about non-Archimedean, a.k.a. ultrametric analysis, which is that unlike in real analysis, in non-Archimedean analysis, a series will converge if and only if its terms go to 0 in magnitude. So the harmonic series, which is the classic example of a series of real numbers whose terms go to 0, but for which the series itself diverges, that cannot happen in the non-Archimedean setting. So from now on, I'm going to write H to denote TQ, where Q is an arbitrary prime number. On occasion, I will use TQ to denote TQ. I hope this as one usually does. So we're going to begin by constructing chi-H, the numen of H. And for both practical and theoretical reasons, rather than just jumping into the construction, I would first like to show everyone So I'll show you all how I stumbled upon it. Doing so requires us to go over the basics of strings, a foundational concept from formal language theory and theoretical computer science. For clarity's sake, just for those formal language theorists or theoretical computer scientists out there, my notation deviates somewhat from the standard conventions. I write my strings as bold letters rather than italics, and I denote string concatenation by a binary operator, in this case a wedge, rather than by mere juxtaposition. So I concatenate I wedge j is the concatenation of I and j rather than ij or just xy. So we begin with the branches. For each j in 0, 1, I write hj to denote the jth branch of h. This gives us two maps, h0 of x equals x over 2, and h1 of x equals qx plus 1 over 2. I call h0 the even branch and h1 the odd branch. So now we're just recall the shortened Collatz map. So the shortened qx plus 1 map accepts an integer n as input and then applies the even branch if n is even and applies the odd branch if n is odd. As a result, given an integer n, its forward orbit under h can be expressed in terms of compositions of h0 and h1. Obviously, the particular composition sequence of h0s and h1s we get depends on what n we started with, and that's the challenge of studying the dynamics of these maps. We have to untangle the relationship between n and its trajectory. To try and crack open this nut, I asked myself the following question. What happens if we consider arbitrary composition sequences of h0 and h1? Well, let's find out. So classically, one of the key statistics associated to the Collatz map, or more generally the shortened qx plus 1 maps, is Terrace's notion of the parity vector. Given an integer x, the parity vector of x under h is the sequence generated by the values of x's iterates mod 2, meaning we take its forward orbit and then we just forget everything except the values of the terms mod 2. Because the value of the kth iterate mod 2 will determine which branch of h we apply when we consider the kth plus 1th iterate, we can say that the parity vector of x encodes x's motions under applications of h. This is a very important object in classical Collatz studies, and it's going to be important in our work as well, but in a non-standard way. So for this example, let's fix q equals 3. Then setting x equals 3, let's consider the first 3 iterates of 3 under h. The first iterate is we apply the odd branch because this input is odd. We get 5. The second iterate is applying h to 3, which gives us 5, which is odd, so we're going to apply the odd branch to 5 to get 8. And since 8 is even, for the third iterate, we apply the even branch to get 4. And so circle 3 of 3 is h0 of h1 of h1 of 3. In this way, given any integer and any k, there is this should be an n, or this should be an x. Given any x, there is a unique sequence of j's such that the kth iterate of x is equal to this sequence applied to x. Since an integer x is a periodic point of h, if and only if there is a k such that the kth iterate of h fixes x, by replacing h with this composition sequence, where the j's are determined by x, we then have the following equivalence. Now, classically, the j's, which are the first k elements of x's parity vector, albeit written in reverse order, classically, this sequence is going to be viewed a posteriori of the value of x that generates it. That is, parity vectors come from a given x's. X is the independent variable, its parity vector is the dependent variable that we get as a result. But what if we reverse this dependence? Instead of treating the j's as something to be derived from x, what if we treat x as something to be derived from the j's? Well, given any finite sequence of zeros and ones, we get our maps, and since they're all affine linear maps, there are going to be constants a and b depending just on the choices of our j's, such that this composition is AR plus B for all rational numbers R. So given this choice of j's and x, we have the following. X is blah, x equals AX plus B, where A and B are functions of the j's. And excuse that. And here, we then solve this to get x equals b over 1 minus a. Here it's crucial that a is not equal to 1, or otherwise this equation will have no solution. Fortunately, this condition is always going to be satisfied. For any given choice of j's, the a here is going to be the product of the a from this and the a from this, so it's going to be aj1 times aj2, yada yada yada. This is going to be a number of the form q to the m over 2 to the n, where m and n are non-negative integers, where n is greater than or equal to 1. Obviously, this is never going to be equal to 1, and so this formula here is always going to have a solution, and it's a unique solution. And so this number then is the unique rational number which is fixed by this composition sequence. To give a concrete example, letting q be arbitrary, consider the composition sequence h1 of h1 of h0 of h1. If we compose all of these maps, we end up getting that this is q cubed over 16x plus q squared over 16 plus q over 4 plus 1/2. Same equal to x, we solve, and we get that if x is fixed by this composition sequence, it must be of the form q squared plus 4q plus 8 over 16 minus q cubed. When q equals 3, this evaluates to negative 29 over 11. And since negative 29 over 11 is not an integer, we can conclude that T3 has no periodic point in Z, which is fixed by this particular composition sequence. So in this way, we can study this phenomenon right here by viewing it as a function of our choice of J's. Since every periodic point of H corresponds to some sequence of j's, to determine the periodic points of H, it suffices to figure out all of the rational integer values attained by x as our choices of j's vary in this formula. So if we consider all possible sequences that occur here, we're going to then, if any periodic point must satisfy this equation for some sequence, and so we'll be able to find all of them. So in and of themselves, these insights are not new. In fact, they are very not new. For the specific case of H equals T3, if we treat the J's as arbitrary and we write this out in full, we will end up getting a Diophantine equation, which is gives us a criterion for periodic points. This was first discovered in 1978 by Bohm and Sontachi. Specifically, this is their formula. It's the way they originally stated it. I like to call this result the Bohm-Sontachi criterion. That's my own terminology. So let X be a periodic point of the Collatz map. So that means not the shortened map, just the original OG Collatz map. Then there are integers mn greater than or equal to 1 and a strictly increasing sequence of positive integers b1, b2, etc. so that x is equal to this sum over 2 to the m minus 3 to the n. More general versions of this formula can be found on K.R. Matthews' slides. So while the existence of a Diophantine equation governing periodic points of Collatz types maps is not new, my approach differs from past work in a key way. Instead of viewing these exponents here as unknowns to be determined, we can, in the manner of this example right here, parameterize those numbers in terms of a single variable, our choices of j's. As we saw, from this particular choice of j, we got this particular rational function. So all of these exponents, instead of being arbitrary, they depend on our choice of j's. So we can parameterize this thing. And specifically, the act of solving this equation right here for x given j's, that's going to give us a function. And it's going to give us a function which accepts a string as an input and produces a scalar as a value. As an output value. A great, just for strings, a great reference is Alouche and Shalat's book, Automatic Sequences. Their first chapter is aptly titled Stringology. I originally made my own notation for this stuff, but I decided to conform it to Automatic Sequences notations just because. So here's the stuff. So let p be an integer greater than or equal to 2. In the theory of automata, one writes sigma p to denote the set 0 to p minus 1. Sigma p star is then the set of all finite sequences whose entries belong to this set. Sigma p is called an alphabet here. The elements of sigma p star are called strings. We also include the empty set as an element of sigma p star and call it the empty string. An arbitrary string j is denoted j1 through jn, where n is the length of the string, and we denote the length by the absolute value signs, and define the empty string as the unique string of length 0. In this way, any string j can be written as j1 through ... j length of j. Also, I say a string is non-zero when it contains at least one non-zero entry. We write sigma p infinity to denote the set of all sequences, finite or infinite, using the alphabet 0 through p minus 1. As with sigma p star, we also include the empty string as an element of sigma p infinity. We call the elements of sigma p infinity strings as well, and say a string is finite or infinite based on whether its length is finite or infinite. So I had not known that strings were a thing. When I wrote my dissertation, I was working in total isolation, and this is the notation that I used in my dissertation. It's still there. This is the conversion. String p, string infinity p. So with strings at our disposal, we can succinctly state composition sequences of the branches of H. So given any string j, we define a finite string, we define the composition sequence h bold j as h bold j of x equals h j1 through j length of j applied to x. And in particular, we're going to identify h empty set, aka h empty string, with the identity map. Now, people have gotten angry at me for doing this because they're going to say, what? Wait a minute, Max. Why are you indexing the map that you apply first last? That seems crazy. I know, but just trust me. This is the nicest way. If you want to do it, you can do it any other way, but it will be messier. So, in particular, in all of this, I'm trying to make this as psychologically comfortable as possible. And so everything we're going to be doing it left to right, left to right. And this approach, the reason why it works is because of our way of writing p-adic numbers. Remember, we have that our p-adic numbers are formal power series, well, p-adic integers are formal power series in the variable p with coefficients here, and then in our digits, we write them left to right in terms of increasing powers of p. So the reason why this is important is because we are going to transform the set of strings into a set of numbers. And what we're going to do is we're going to identify the digits of a given string, or the entries of a given string, with the digits of a p-adic integer. Specifically, we're going to identify z with the string whose elements are its digits. And we're going to do this with the help of a function I call digit sum, introduced below. Given an integer p, I write digit sum p to denote the function which accepts a string of infinite or finite length and outputs the p-adic integer, where we take the j's and we add them in order. So the same order that we write the j's is the same order that we write the digits of our p-adic integers. The details of our identifications are as follows. So identifications with the non-negative integers. Given j of an infinite string and given a p-adic integer z, I say j represents or is associated to z and vice versa, written like this, whenever j is the sequence of the p-adic digits of z. That is, z twiddles j if and only if j twiddles z, if and only if z equals j1 plus j2p plus j3p squared plus blah blah blah. Equivalently, j twiddles z if and only if the digit sum p of j is equal to z. We then observe that Twiddle introduced that this identification is an equivalence relation on both of our string sets. In particular, we say that two strings are equivalent whenever, this should be dig sum p, my bad, my bad. We say two strings are equivalent whenever they represent the same integer. So this is something important. If I have an integer, a rational integer, it's going to have only finitely many p-adic digits. So, for example, in the q-adics, the integer 3 is represented by the sequence 1, 1. However, using digit sum 2, note that the string 1, 1, 0 also represents 3. That 0 represents 0 times 2 to the second. But since it's 0, it doesn't count. So 1, 1, 0 represents 3. 1, 1, 0, 0 represents 3. 1, 1, 0, 0, 0 represents 3. And you get the idea. And what ends up is this equivalence relation. It deletes any zeros at the right end, any terminal zeros. And in particular, with this equivalence relation, every integer, whether p-adic or rational, as long as it's greater than or equal to 0, it has a unique shortest representation. And then we get into the following equivalences. So the set of equivalence classes of the finite strings and infinite strings under this relation are in bijective correspondence with n0 and zp. So finite strings in base p modulo representational equivalence gives us n0, and infinite strings in base p modulo representational equivalence gives us the p-adic integers, and the projection from these sets onto these sets is, well, not the projection, but the bijection is the map digit summed. So two finite strings are equivalent if and only if we can attain one of them by adding or removing zeros to the right of the other. And then given a finite string and an infinite string j, I can be Twiddle's j if and only if j contains finitely many non-zero entries. These are all immediate from definitions. So, from an algebraic point of view, strings are useful because we can concatenate them. And so this leads us to the concatenation operator, which is, I define it wedge. It accepts two infinite strings and outputs an infinite string. And the rule is as follows. If the left string is of finite length, then it's just the concatenation of first all the digits of the left string and then all the digits of the right string. Whether or not the right string is finite or infinite, this doesn't matter. But if the left string is infinite, then we define this as a wedge as just being the left one. Additionally, for any integer m, any finite string, I write j to the wedge m to denote the concatenation of m copies of j with itself. So here's just a fun exercise. As we saw, we can identify infinite strings with p-adic integers. In that respect, we can then use this operation to define a binary operation on the p-adics by saying that that a wedge b is equal to the number represented by this wedge of their respective strings. It's a fun exercise to show that this operation is not continuous with respect to the topology of the p-adic integers. Equipping our string sets with concatenation makes them into monoids. In particular, it makes them, the empty set is the identity element, and this is a non-commutative monoid. For us, strings are useful precisely because our notation for composition sequences is itself a homomorphism of monoids. This suggests it may be interesting to explore how the methods of this part of the video apply to the study of arbitrary sequences of compositions of maps on a Q, but like polynomials, for example, instead of affine linear maps, but that's beyond the scope of this video. So here's the why we like string notation. H of I wedge j is H of I applied to H of j. In other words, our notation turns wedging into compositions. And the proof is we just write out the definitions. We have this and that. It's by definition of our composition sequences, and voila. Before moving to the next section, I just need to remind you of two important arithmetic functions. First, we have the number of bits, which is the number of q-adic digits in n, and any integer n greater than or equal to 0 can be uniquely written like this for zeros and ones as the c's. And note that the lambda 2 of n is always going to be less than or equal to the length of any string representing n. In particular, the shortest string, j, which represents n, is going to have a length of lambda 2 of n. Next, for each n greater than or equal to 0, I write the number of ones of n to denote the number of ones present in n's q-adic expansion. In an abusive notation, I'm going to use number of ones to also denote the number of ones in a given string. So number of ones of j is the number of ones of j. And we have the following functional equations. The number of ones of 2n times a plus b is the sum of the number of ones of a and b. This does not work if n is 0. And the number of digits in 2 to the n a plus b is number of digits in a plus n. This does not work if a or n is 0, and the proof is a straightforward computation. So, with all that done, we can now actually get to the work of constructing our numen. So, with strings at our disposal, we can actually properly analyze this equation here. To begin, what we're going to do is replace this with our sequence j, and so this is then the map hj. And for a rational number r, just by slope-intercept formula or Taylor series, this is always going to be hj of r is h prime j of 0 times r plus h j of 0, and this holds for all finite strings and all rational numbers. Since this is an affine linear map, note that this derivative is going to be a constant, which in fact it's independent of what we evaluated at. Next, so viewing the bold j as the instructions for how to apply the branches of h, observe that if x is a periodic point of h, it is then necessary that there is some string j of length greater than or equal to 1, such that hj of x equals x. If x is a periodic point, there has to be some sequence of maps, of compositions, of some sequence of branches whose composition, when applied to x, sends x to x. So plugging this into the formula here gives us x equals h prime bold j of 0x plus h bold j of 0. Since h prime j of 0 is not equal to 1, for all j, the chain rule tells us that this is going to be a product of h prime j of 0 for all the j's in bold j, and so this constant is going to be not equal to 1, and so we can solve this, and we get the unique value that x is, if x is a periodic point, then it's going to be of the form h bold j of 0 over 1 minus h prime of bold j of 0. And this is also we need here for x to be non-zero. So the existence of such a j is a necessary condition for x to be a periodic point of h, and this is precisely what Baum and Sontachi found. However, we're going to take things further than that. The significance of this formula is that it gives us a formula for the unique fixed point of h bold j in terms of our string variable j. So instead, let's view this as a map which accepts bold j as input and outputs this rational number. By using the digit sum function, we can identify the bold j's with non-negative integers, and later with q-adic integers. We can then study this right-hand side analytically, first as a function of a non-negative integer variable, and later as a function of a q-adic integer variable. Now, while we could analyze this whole thing, this turns out to be less than ideal because of the denominator here. A simple computation shows that the value of h prime bold j of 0 is q to the number of ones in j divided by 2 to the length of j. And so This expression here, the right-hand side is going to blow up for values of j, which makes this fraction close to 1. In particular, by taking logarithms, this is values of j, which will make this real number close to 0. Controlling the size of this number would take us directly into transcendental number theory, specifically Baker's theorem on linear forms and logarithms, a can of worms in its own right, as we will see later on. So, in attempting to study this, instead of trying to deal with the whole thing, let's just consider the numerator, the function which accepts bold j as an input and outputs the constant term of h bold j. This is I call this function the numen, and I denote it by chi q, or in this case, chi h. Chi q, chi h. Forgive me for not being consistent. So this is what happens when I type things at light speed. So the numen of the shortened qx plus 1 map is the function chi q, which accepts a finite string in base 2 as input and produces a rational number as output, defined by the formula chi q of bold j equals h bold j of 0. Since h empty string is the identity map on q, this then tells us that chi q of the empty string is 0. So this is when we view things just in terms of strings. But what we want to do is pass from strings to numbers using our digit sum function. To show that this is possible, all we need to do is show that chi q of bold j, it can be defined independent of the equivalence relation. It's well defined with respect to this equivalence relation, and that's what we're going to show right here. That is to say, if I and j represent the same integer, then applying chi q should give us the same value for both. So let j be any non-empty string. Then, by proposition 14, our notation, chi q of j wedge 0, where 0 represents the string containing the entry 0, this is going to be h bold j wedge 0 of 0, which is h bold j of h0 of 0. But h0 fixes 0. It's just h0 is x over 2. So this is the same thing as h bold j, and that's, by definition, chi q of bold j. So, concatenating zeros to the right of bold j does not change the value of chi q. As we saw, any two equivalent finite strings can be obtained from one another by concatenating finitely many zeros to the right. So this then tells us, just by induction, without loss of generality, suppose I is j with then n zeros to the right of it. Then, by this result, we get the following, and it's equal to chi q of j. So, chi q is well defined on strings modulo representational equivalence. So, this then allows us to define chi q as a function on the non-negative integers, where we define chi q of n is chi q of bold j, where bold j is any string representing n. In particular, we are treating the empty string, it represents 0. This then tells us that chi q of 0 is 0. And the proof is by our proposition, which shows that chi q is well defined with respect to this equivalence relation. So, although we will eventually shelve the string formalism in favor of treating chi q as a function on n0 and later z2, strings have the advantage of greatly simplifying the proofs of the results that we need to get our analysis off the ground. As such, for the remainder of this section, I'm going to maintain a bilingual dictionary, expressing everything in terms of both strings and the numbers represented by those strings. So first, we're going to deal with that h bold j prime, that troublesome term from our denominator from earlier. We're going to define mq from n0 to q as mq of n by definition is mq of bold j, which is then of course h bold j prime of 0, where j is the shortest element of sigma star 2 representing n, and I define mq of 0 or the mq of the empty string to be 1. So here, unlike chi q, mq is not well defined over this equivalence classes. For example, consider the strings 0, 1 and 0, 1, 0. Both of these are sequences of 2-adic digits of the integer 2. However, H01 has its slope is q over 4, but H010 has its slope is q over 8. So even though these two strings are the same, the values of MQ at those strings are different. And so this is another reason why we don't want to study that full fraction, because this is badly behaved. So with these identity definitions in place, we can now use strings to establish the most important result in all of my work. It's these functional equations. I will call them the concatenation identities, specifically when talking about strings, or just the functional equations. So first, we're just going to work through the details. H bold j of x is equal to mq of bold j times x plus chi q of bold j times chi q of bold j. This is just by definition of what this means and that means. So then here's the concatenation identity for chi q. Chi q of I wedge j is hi of chi q of j. That is to say, for any bold I equals I1 through IM, if we look at this input integer as the first it's a number, its first m q-adic digits are the entries of I, and then it's plus 2 to the m times something else, this is going to be equal to h bold I of chi q of n. So here, let I and j and x be arbitrary. H of I wedge j of x, well, that's h prime of I wedge j of apply at 0, this plus h I wedge j at 0. This is just Taylor's formula. And then here we rewrite the definitions. H bold I, this is going to become h bold I of h bold j of 0. So therefore, these two expressions are the same. So this thing is equal to that thing. And by definition, this is h bold I of chi q of bold j. And this is chi q of bold I wedge bold j. The proof for MQ's concatenation identity is similar. Here, notice that MQ is a monoid homomorphism, again, but it's a different monoid. Instead of turning concatenation into composition, MQ turns concatenation into multiplication. And the proof is exactly the same. We just write out everything from the definitions. Since hi wedge j is hi of wedge j, if we differentiate both sides with respect to x, the chain rule tells us that this is h prime of I wedge j of x is h prime I of hj of x times h prime of j, and now we set x equal to 0. This is mq of I wedge j, this is mq of j. And here, we note that since hi is an affine linear map, its derivative is a constant. So what we evaluated at doesn't matter. We can replace this number on the inside here. We can just replace it with 0, and that's then going to be mq of bold I. Now we're going to restate these functional equations as systems of functional equations. And here, this is where 2n plus j is equal to aj over 2. And note, this is not going to work when 2n plus j is equal to 0. So we need to have 2n plus j is non-zero. And here aj is 1 when j is 0, and is q when j is 1. And then so let n be greater than or equal to 1, and let bold j be the shortest string representing n. Then, so picking another digit, and concatenating it at the left, set bold k to be this. We then have that k represents j plus 2n, and that j wedge bold j is bold k. So by proposition 18, mq of 2n plus j is mq of j plus wedge bold j, which is the product, and then by definition, mq of j is going to be aj over 2, because j is either a 0 or a 1. And as an example for the exceptional case, 2 times 0 plus 0 is 0, and that's equal to 1, but the right-hand side of this formula is equal to 1/2. Next, we state chi q's functional equations. What makes these equations and this identity so important is they actually provide a complete characterization of chi q as a function on the integers. Chi-q is the unique function from the non-negative integers to the rationals, satisfying this system of functional equations, that chi-q of 2n plus j is the same thing as applying hj to chi-q of n, which can also be written like so. And remember, in episode 1, we proved these functional equations from the F-series representation. The proofs are very nice. So, first, show that chi-q satisfies the system of equations. Let bold I represent n, and let j be 0 or 1. Then 2n plus j is represented by j wedge bold I, and so by the concatenation identity, chi-q of 2n plus j is equal to chi-q of j wedge bold I is equal to hj of chi-q of bold I is equal to hj of chi-q of n. Thus, chi-q is, since n and j were arbitrary, this shows that chi-q solves these functional equations right here. The reason why we need not exclude the n equals j equals 0 case here is because h0 of chi-q of 0 is h0 of 0, which is of 0, which always works. Now, uniqueness. So let f be any function on n0 and rational value satisfying this functional equation. Setting n equals j equals 0, and since it's rational, gives us f of 0 equals f of 0 over 2. Since it's rational valued, this forces f of 0 to be 0. And so plugging in n equals 0 then gives us f of j equals hj of 0. Upon writing any integer n in its q-adic Hensel series form, we see that the identity f of 2n plus j equals hj of f of n is then equivalent to the following. So we're just going to use that formula from before. We pull out the j1, and then we divide by 2, pull out j2, divide by 2, blah, 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 blah. We get this. F of 0, as we saw, is 0. And so f of this integer is h of that. And so for any string bold j prime, we have that h of bold j prime is h of bold j prime of 0, which by definition is chi-q of bold j. So if f solves the given system of functional equations, f of bold j equals chi-q of bold j for all bold j, and so f of n equals chi-q of n for all n, which proves uniqueness. Boom. So next, we compute explicit formulae for mq and chi-q in terms of the constants associated to h. Aside from being satisfying in their own right, they let us make the q-adic estimates we will need in order to prove that chi-q can be extended from a function from n0 to q to a function from the 2-adic integers to the q-adic integers. Specifically, mq of n is q to the number of 1s in n over 2 to the number of bits of n, which an mq of bold j is q to the number of 1s in j over 2 to the length of j. I omit the proof because this proof is going to be in the next proposition. The main thing to note here is that when we take q-adic absolute values, we get that mq of bold j has a q-adic absolute value of q to the negative number of 1s in bold j. So as the number of 1s in j tends to infinity, mq of j will decay q-adically to 0. So proposition 21, we have the following formula for chi-q of bold j, and this product here will be defined to be 1 when m equals 1. The proof takes from writing out this formula and then doing a glorious computation. So we put everything out, and we have this, and then we have the pattern, and we note the pattern, and then we see that this is mq of bold j by mq's functional equations, and this is chi-q of j, where we, as we said, we've used the convention that this product is 1 when m equals 1. I will leave that up there for a moment. So now we have everything we need for the main result of this subsection. The proof of the existence of a 2q-adic continuation of chi-q, and the characterization of this extension by a system of functional equations and a rising continuity condition. So here's lemma 4. This limit, which is taken, so it's the limit of chi-q of z mod 2 to the n, converges q-adically to chi-q of z, and if this then defines, this right-hand side defines this quantity, which is going to be a function from z2 to zq. Moreover, this extension is continuous on z2 prime, which is the set of all two-adic integers with infinitely many digits. Moreover, for all z and z2, the functional equations hold, and the extension chi-q defined by this limit is the unique 2q-adic function satisfying this system of functional equations subject to this rising continuity condition. So first, we're going to show the limit here exists. If z is a non-negative integer, then z mod 2 to the big N will be equal to z for all sufficiently large n. So if z is a non-negative integer, this sequence is going to eventually become just a constant sequence once n is sufficiently large. So this sequence will converge in the discrete topology when z is a non-negative integer. Thus, the limit exists for those z. So all we have to do is assume z is in z2 prime and then show the convergence. So let z be in z2 prime and let bold Jn be the shortest string representing z mod 2 to the n. That is, z mod 2 to the n is this sum. By our lemma, where is it? Never mind, it's sad. I won't scroll back. So by our lemma, I will scroll back. So 174, here. So by this thing, chi-q of n is equal to chi-q of bold j. By that thing, we have that, and we're scrolling back, that chi-q of bold j is going to be it's going to be this limit, because this is chi-q of z mod 2n is chi-q of the string representing z mod 2n. And then by definition, this is going to be h bold jn of 0, which using our explicit formula is this sum. So it's m equals 1 to the number of terms in bold jn of b jm over 2 times the product of ajk over 2 from k equals 1 to m minus 1, where the product is defined to be 1 when m equals 1. When with proposition 20, which is with this result, which gives us our formula for mq, we can then say that this quantity right here is exactly mq of bold j of m minus 1. Remember, mq, this is by the functional equation. So we can rewrite this expression as the following sum. So taking limits, formally, we get that this limit as n approaches infinity, its limit as n approaches infinity of this. So we're going to consider the string that you get when you project z mod 2 to the n. We're then going to figure out mq of z mod 2 to the m minus 1, and then multiply it by bjn. The bj's are going to be 0 or 1 based on whether jm is 0 or 1. So if we take the q-adic absolute value of this expression, since q is odd and 2 is even, this is less than or equal to that, which as we saw is q to the number of 1s in jm minus 1. This is the number of 1s in z mod 2 to the m minus 1. Since z is in z prime, z has infinitely many two-adic digits, and so the number of 1, it's going to have infinitely many 1s, and so the number of 1s in the string representing z mod 2 to the m minus 1 is going to tend to infinity as m goes to infinity. So that means this number goes to infinity in the real topology, so this number goes to 0 in the real topology, so this number here goes to 0 in the q-adic topology. So that this then guarantees the convergence of this series q-adically, because when n goes to infinity, you get mq of bold jm minus 1, which converges to 0 q-adically as m goes to infinity. So that proves the convergence. So to prove the 1 here, that it satisfies this functional equation, we're going to use our functional equation for chi-q over the integers. So so we're going to consider just this thing right here. Just consider chi-q of z mod 2 to the n. That's an integer. So by the case for integers, we get that chi-q of 2 times z mod 2 to the n is equal to chi-q of z mod 2 to the n over 2, and likewise for the odd branch. In other words, what we have is that, moving ahead, boop, 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 yes. So we can take limits of the functional equations because the maps here, h0 and h1, these are affine linear maps, so they're continuous on QQ. So this functional equation, it holds for z mod 2 to the n, and then we just let n go to infinity and use the continuity of the branches, which then gives us the convergence we want. That proves that this equation is satisfied by for all q-adic integers z. So this is just a standard argument. If you have a rising continuous function and it satisfies a system of functional equations like this over the integers, if your rising continuous function extends to a 2 q-adic function, then so will its functional equations. It's very nice. So for 2, to show the uniqueness, we're going to show that suppose f satisfies these functional equations and is rising continuous. Then the restriction of f to n0 must be equal to chi-q. If s satisfies these equations for all q-adic integers z, it necessarily satisfies these equations for all non-negative integers z. And so, as we just saw, that then forces f to be equal to chi-q on the non-negative integers, which by rising continuity then forces the extension of f to be a 2 q-adic function to be equal to chi-q's extension. And so this extension is unique, and that's that. And we are done. So note that when we were considering this limit, a dichotomy arose. If z was in n0, this sequence would converge in the discrete topology. And since the discrete topology is the coarsest possible, or is the finest possible topology, that means this limit is then going to converge in any other topology we can think up of on Q or an extension thereof. On the other hand, if z is in z2 prime, the topology only works if we choose the q-adic topology. So this is frames showing themselves before we've done anything anywhere. And so now we have the road to the correspondence principle. And here, one moment, I am going to take a break. So just give me a moment here to remember how to do this. Okay, we have, I do that. And we're back. I forgot how to pause it, so I'm going to start a new recording. But now I remember how to pause it, so I won't need to start another one after this. But whatever, I'll stitch them together. Fine. So, road to the correspondence principle. Having constructed chi-h, also known as chi-q, again, apologize for the inconsistency, we now turn to establishing the correspondence principle. Here, the main result is the CPPP, the correspondence principle for periodic points. The CPDP, the correspondence principle for divergent points, will occur as a simple corollary of the CPPP, so I'll focus the exposition on the periodic point case. The main idea is that for any x in the integers and any integer L greater than or equal to 1, there is a unique string, bold J, of length L, such that applying H bold J of x is the same thing as applying H itself to x L times in a row. This J, of course, is the one that encodes the movements of x under H. So let's get started with the preparatory work. Obviously, the CPP has an if and only if statement, and that means we have two directions to prove. The preparatory work for the proof will tackle each of these one at a time. In both of these cases, I'm going to explain what we're going to do before we actually get to the preparatory work. So for the first direction, we're going to start with a non-zero integer x, which is known to be a periodic point of h, and it generates a cycle big omega of length L. Then, since x is a periodic point, there's going to be a unique string j of length L, such that h circle L of x is equal to h bold j of x. Now, since x is a periodic point, obviously, x is going to be fixed by not just h circle L, but by h bold j. In particular, so that means that if we forget about h itself and just look at h bold j, this particular choice of branches fixes x. So x is a fixed point of h bold j, which means we can repeatedly apply h bold j to x without changing anything. H bold j of x, as is h bold j circle 2, as is h bold j circle 3, etc. And so we have h bold j to the circle m of x is equal to x. Now, we iterate the Taylor series or slope-intercept formula for h bold j of x, and we can then express this mth iterate in closed form in terms of this and that. We get that h bold j iterated m times at x is the mth power of mq of bold j plus this fraction times x plus this fraction times chi q of bold j. And since x is a non-zero periodic point, this is going to be equal to x. Here's the key detail. Since x is a non-zero periodic point of h, j must contain at least a single 1. Otherwise, a bold j is a zero string, and so h bold j is just going to divide by a power of 2. Therefore, if x being fixed by h bold j forces x to be 0. So j has at least 1 1. Thus, mq of bold j has a q-adic absolute value that is strictly less than 1, because it's going to be q to the number to negative, it's going to be q to the power of negative number of 1s in bold j. So that means mq of bold j to the m is going to decay q-adically to 0 as m approaches infinity. So letting m approach infinity, x is going to be equal to this goes to 0, and this goes to 0, and so we get that x equals chi q of bold j over 1 minus mq of bold j, which by definition is of these two functions is our old friend from before that we got from solving for the fixed points. So to get something useful out of this, we note that this is not the only way to express this composition sequence in ax plus b form. Instead of using the Taylor series, we can use the concatenation. H circle m of bold j, applying that map the same m times, is the same thing as applying the map h bold j to the wedge m. And then by definition, this is mq of bold j wedge m and chi q of bold j wedge m, where recall chi q bold j wedge m is the concatenation of m copies of j. Since mq is a homomorphism of monoids, which transforms concatenation into multiplication, we get h bold j of circle m of x is equal to this. So setting this equation equal to this equation gets us the m power of mq of bold j times x plus chi q of bold j to the wedge m equals mq of bold j to the power of m times x plus this thing. So if we cancel this common terms, we're left with this thing. As we saw, the right-hand side converges q-adically to this as m goes to infinity. So for any string j containing at least 1 1, and again, chi q is the same thing as chi h, we get chi q of bold j to the infinity. But what is this? this is the same thing as the well, what is this? This is a q-adic. This is a q-adic integer, which we can then, so by definition, using the rising continuity, this is going to be the limit as n approaches infinity of chi q of bold J wedge M, which is going to then converge q-adically. So what this is saying is that when we go from extend chi q from finite length strings, that is from non-negative integers, to infinite length strings, we can recover our fraction from chi q. So letting I be the string obtained by concatenating infinitely many copies of bold J, we have the following. So this then tells us that, so remember, and we saw that this formula is equal to our periodic point, x. So if x was a periodic point, where J was the sequence of motions that move x around the cycle once, it then turns out that chi q of this thing is equal to this quantity, which is equal to x. So x is a value attained by chi q over the two adics. That gives us the first half. The takeaway from this preliminary analysis tells us where we need to first look. We need to look at what happens to a given finite string, bold J, when we concatenate it with itself, and how doing so affects the integer represented by this string. And that's what this next proposition is. Let J be the shortest string representing a positive integer n. Then the integer represented by m concatenations of bold J is n times 1 minus 2 to the m lambda 2 of n over 1 minus 2 to the lambda 2 of n. The proof, well, since n is a non-negative integer, we can write it like, actually it's a positive integer, we can write it like this, where these entries here are, of course, the entries of the string bold J. And so just by writing out, concatenating this m times, we write that out as q-adic has a Hensel series. And so we have, here's the original n, and then here's what we get when we multiply, the second copy of bold J is going to be shifted by a factor of 2 to the lambda 2 of n. The third copy is going to be shifted by a factor of this squared, etc. And then when we gather it all up, we get that each of these is n, so it's n plus n times the first shift plus n times the second shift, and then summing the geometric series gives us the desired result. So the key step in our preliminary analysis was that when we considered the behavior of chi q of bold J wedge M as M approached infinity, and as long as J was not the zero string, the rising continuity of chi q told us that the behavior of this limit is the same thing as what happens when we precompose chi q with the map which accepts a finite string and outputs the infinite string obtained by concatenating your string, your infinite with itself infinitely many times. I call this map B2. Its definition over strings is that we take a finite string and then output the infinite string that's J concatenated with itself infinitely many times. In terms of n, in terms of n, if we identify everything with with their integers, we get that b2 of n is 0 if n is 0. And using this thing as m approaches infinity, it converges q-adically to n over 1 minus 2 to the lambda 2 of n. So b2 sends n to the q-adic integer whose sequence of q-adic digits consists of infinitely many concatenated copies of n sequence of q-adic digits, and where the convergence is right here. So here's the thing. Let bold J be a non-zero string, and let n be the integer represented by bold J. Because the sequence of the q-adic digits of b2 of n is the concatenation of infinitely many copies of bold J, observe that for each integer k greater than or equal to 1, this string represents the b2 of n projected mod 2 to the k bold J. In other words, for any, and as a result of this, for any f which is rising continuous, the limit as k approaches infinity of f of bold J wedge k converges q-adically to f of b2 of n. Because again, projecting the limit here, modulo 2 to the k bold j, is the same thing as only concatenating k copies of bold j in the first place. Also, note that B2 can be extended to a function on Z2, which is defined as the identity map on Z2 prime, meaning it will fix any, it fixes every q-adic integer which has infinitely many digits, and then we apply this formula if our q-adic integer is a non-negative integer. And this then makes B2 into a projection, that is an idempotent, because then B2 of B2 is the same thing as just applying B2 the first time. So with B2 at our disposal, this behavior of chi-q of bold j, as we concatenate j with itself infinitely many times, can be realized as an instance of a functional equation for chi-q of B2. This then allows us to recover our the denominator formula that was here that was too messy to work with. It allows us to recover it completely. And so the equation is this. Chi-q of B2 of n is equal to chi-q of n over 1 minus mq of n for all n greater than or equal to 1. This equality is just worth talking about it for a little bit. So in just viewing these as numbers, for every positive integer n, this is some number, and this is some number. They're both going to be rational numbers, but in fact, they're not just any rational numbers, but they're rational numbers whose denominators are co-prime to q, which makes them q-adic integers. Additionally, if we write out the infinite series formula for this thing, it will converge q-adically. So now, to prove this, let n be in n1, a positive integer, and let bold j be the shortest string representing n. Note that since n is greater than or equal to 1, bold j contains at least one 1. Now, for all m and n greater than or equal to 1, I don't know why I used two different notations here, but whatever, we have that applying h bold j to the wedge m to the k is the same thing as applying h bold j to k m times. Now, as we did in the preparatory work, note that for an affine linear map of the form ax plus 1, if you apply the geometric series and induction, you can prove that the function produced by m iterations of this thing is a to the m x plus 1 minus a to the m over 1 minus a times b. So since h bold j is an affine linear map, h bold j of k is equal to mq of bold j times k plus chi-q of bold j. And so then this gives, by applying this equation, if we iterate it m times, we get this. Noting also that h bold j wedge m is like this, we then equate our two formula like this. And by proposition 18, mq turns wedging into multiplication, and so we can cancel those terms, and we're left with the following equality. We have this thing is equal to this thing, which is then equal to this, where we've rewritten these quantities in terms of n. By proposition 22, the one that gave us our explicit formula for bold j to the wedge m, that's going to be chi-q of bold j to the wedge m is a rational number, which is the same thing as n times 1 minus 2 to the m lambda 2 of n over 1 minus 2 to the lambda 2 of n. Whereas indicated, the equality occurs in q. Next, we note that, as we mentioned, as remarked earlier, this is what we get from concatenating infinitely many copies of bold j. So, if we project it mod 2 to the m, that means we're only concatenating m copies of bold j, which means b2 of n modulo 2 to the m is precisely this number. In other words, going back to this equality, we have this thing here is equal to chi-q of bold j to the wedge m is equal to chi-q of that, and this is chi-q of b2 of n mod 2 to the m. Now we use rising continuity. As m goes to infinity, this is going to converge q-adically to this quantity, And as m goes to infinity, this thing is going to converge q-adically to here, because mq of bold j has a q-adic absolute value less than 1, because bold j has at least 1. So this here converges to that, and that q-adically, and this converges q-adically to that, and we're done. This functional equation is a generalization of the Bohm-Sontachi criterion that we saw earlier. The fraction here on the right-hand side, if you write it out in using that formula we saw for chi q of n and the formula for mq of n, and we'll do this later, if you write this all out, you'll then get the Bohm-Sontachi Diophantine equation, but those exponents, instead of being arbitrary numbers, they'll all be functions of n. So this is that parameterization I promised. So with that done, now let's get ready for the second direction. So this time, instead of starting with a periodic point, we're going to begin with a string of bold j of length greater than or equal to 1. And we're going to assume that it has at least 1 in it. Putting h bold j in ax plus b form, we have this, where m, and again, the h should be q, but whatever. So because bold j is greater than or equal to 1, as a result, h bold j is an affine linear map whose slope is not 0 or 1. So it's going to have a unique rational fixed point, which is given by this thing. Obviously, if x0 is not an integer, it cannot be a periodic point of h. What we want here then is to show that if x0 is an integer, then it must be a periodic point. To arrive at this conclusion, what we're going to need to show is that fixed points of a composition sequence h bold j, which are integers, are going to be periodic points of h itself. As we'll see, this boils down to formalizing a notion of the correctness of bold j. To get an idea for how to do this, let's go back to the question that motivated all of this, which is, what happens if we consider arbitrary composition sequences of h0 and h1? In the classic view based on parity vectors, as we recall, the sequence bold j, which governs the motions of x under h, is determined by x itself. We can use this to get our notion of correctness. Given an integer x, we will say bold j is correct if h bold j, which is, note, is a composition sequence of length of j maps, sends x to the same place that h itself would send x after applying h a total of length j times. In symbols, bold j is correct precisely when h bold j of x is equal to h to the circle length of j of x. A wrong string, on the other hand, would be a j for which these 2 points are different. So the one thing to note is that for any given x and any given length L, there is a single unique string, j, which makes this true, and for all other strings are going to be wrong. So once we have this idea of correctness, they're going to proceed by the following argument. We're going to show that j is correct for x if and only if h bold j sends x to an integer. That is to say, the correct string to pick is whichever string will get you to an integer output. And in particular, we're going to show that if you do not have the correct string, you will never be able to get to an integer output. And moreover, this follows by showing that once you arrive at a non-integer output, you will never be able to return to an integer by further applying the branches of h. So to do the second round of preparatory work we're going to need to consider the extension of h, that is tq, to the 2 adic integers. This is a well-established procedure in Collatz studies. The extension h on the 2 adics is defined by h of z will send z to z over 2 if z is even, and send z to qz plus 1 over 2 if z is odd. Note then that h is continuous on z2. Moreover, the branches h0 and h1 are continuous functions on q2, and the same applies to h bold j for any finite string bold j. Now, before we continue, it is worth thinking about this extension in terms of completions of number fields. Our setup has h as a map h, which we've defined on Z. Z is the ring of integers of the field of rational numbers, and the branches of H are affine linear maps on the rational numbers. These are necessarily, and moreover, these aren't just any affine linear maps, they're bijections. So if we go further and equip Q with the discrete topology, or which is the same thing, the topology induced by the trivial absolute value, which assigns the size 0 if the input is 0, and outputs the size 1 if the input is non-zero. If we equip Q with the discrete topology, the branches of H will be continuous bijections of Q. That is, they're homeomorphisms. In particular, given any prime number L, when we then complete Q with respect to the L-adic absolute value, the branches of H will become homeomorphisms of QL. Moreover, given some branch, Hj, depending on our choice of the prime number L, it might be the case that Hj is not just a homeomorphism of QL, but is a homeomorphism of ZL, meaning that Hj sends L-adic integers to L-adic integers. Even though the whole map H itself will only admit a straightforward extension to the L-adic integers in the case where L equals 2, and indeed, the branches of H H do extend, which means that we can freely examine any composition sequence H bold J, not just as a homeomorphism of Q, but as a homeomorphism of QL for any prime L. This fact will play a key role in the 11th hour of our proof of the CPPP. And of course, the reason why H cannot be extended to ZL for L not equal to 2 is because there's no meaningful way to define the value of an L-adic integer modulo 2 if L is not equal to 2. So there's no way to determine what branch of H we should apply to a given input if the input is not a 2-adic integer. This whole phenomenon here is, again, it's very frame theoretic. We have this function, in this case, the branches of H, which are defined on our global field, Q, and then we study them by considering their behavior in various different completions of our global field. Anyhow, so we'll begin our second round of preparatory work by defining what it means for a given J to be wrong. So now here's a definition of wrong values and seeds. We say a 2-adic number y in Q2 is a wrong value for H whenever there is a finite string bold J and a 2-adic integer z, such that H bold J sends z to y, but H bold J of z is not the same thing that you would get if you apply H itself to Z J times. That is to say, wrong values are numbers that we get by applying a sequence of branches to Z other than the ones that Z itself would dictate. I then call Z the seed of Y. So here, this is something important to note, is that if Y is a wrong value with seed Z and string J, so that Y is equal to H bold J of Z, note that for any other finite string, if we apply H bold I to Y, we will also get a wrong value with seed Z, right here, because instead the string will not be J, but I wedge J. Thus, branches of H send wrong values to wrong values. So once you arrive at a wrong value, you can never leave it. The lemata that we will need to express this fact analytically come in terms of describing how H bold J affects non-integer 2-adic numbers. This is Q2 take away Z2 instead of all 2-adic numbers with a 2-adic absolute value strictly greater than 1. And so our first proposition is that if your input has a 2-adic absolute value strictly greater than 1, then Hj will produce an output that has 2-adic absolute value strictly greater than 1. So let y have an absolute value strictly greater than 1. Then h0 of y is y over 2, which is 2 times y's q-adic absolute value, which is greater than 2. So this is going to be in q2 take away z2. On the other hand, if we apply the odd branch, we get this. And since y has a q-adic absolute value greater than 1, and since q has a q-adic absolute value of 1, this is going to be greater than 1. So the ultrametric inequality, I suppose that was another prerequisite that I should have mentioned. The ultrametric inequality says that if this number and this number have different q-adic absolute values, then the q-adic absolute value of their sum is equal to the q-adic absolute value of whichever one's larger, which in this case is that, which is that, and that's then going to be, so this is then equal to 2 times that, which is greater. So not only does the branches of H send Q2 take away Z2 into Q2 Z2 take away Z2, but it's actually an expanding map. It's going to make the inputs q-adically larger. And now we have the promised correctness lemma. So all wrong values of H are elements of Q2 take away Z2. So let Z be a q-adic integer, let I be either 0 or 2, and suppose that I is not the value of Z mod 2. Then, by the definition, then we can ignore the definitions for leftover from I should have fixed that. But anyhow, as we saw right here, this is going to have absolute value greater than I'll explain this. So since this is the wrong map, this is going to end up having a 2 absolute value greater than 1. If, for example, if Z2 was even, and we chose I equals 1, then this is going to be an even integer plus 1 over 2, which is not, this is going to be odd, and odd over 2 has a q-adic absolute value that's greater than 1. On the other hand, if Z was odd, and then we picked I equals 0, this would be hi of Z would be Z over 2, which is again odd over 2, which has a q-adic absolute value greater than 1. So by proposition 23, this inequality right here, this forces H bold J of Hi to be an element of Q2 take away Z2. Since every wrong value Y with a seed Z is of the form Y equals H bold J of Hi of Z for some bold J and some I with I not equal to the parity of Z, this shows that every wrong value of H is in Q2 mod Z2. Because basically, once you get the first branch wrong, you arrive in Q2 mod take away Z2, and then by this proposition, once you're in Q2 take away Z2, any branch you apply will keep you in that set. So the wrong values are always going to be in Q2 take away Z2. Now we have the next proposition, the next lemma, which says that let Z be a q-adic integer and let bold J be a finite string. If bold J is correct, that is, if H bold J of Z is equal to Z, then H is correct. So if H bold of Z is equal to Z, then applying H length J times to Z also fixes Z. That is, Z is a periodic point. So let Z and J be as given, with Z equals H bold J of Z. So by way of contradiction, let's suppose that this occurs, so that this equality fails. Then Z is equal to this thing, and Z is not equal to this thing. So these two quantities here must be different. This makes H bold J of Z a wrong value of H with seed Z. By lemma 6, this makes Z into a Q2 take away Z2. However, H bold Z of Z was equal to Z, and Z was given to be in Z2. That's impossible. So consequently, H bold J of Z equals Z necessarily implies that this is true. And that completes the preparatory work. So Though the summaries, now we get the proofs. So though the summaries described in the previous subsections are hopefully straightforward, the actual business of proving the CP is a bit more delicate. The proof is done in 3 stages, the last of which, Corollary 2, is the version that we saw in episode 2. So the first version we're going to prove is Theorem 4. The correspondence established by Theorem 4 is slightly weaker than Corollary 2, what we saw in Episode 2. What we saw in Episode 2 was that there was a correspondence between the values attained by chi-q for 2 adic integer inputs and the periodic points of H. The theorem we're about to prove instead is going to give a correspondence between the values attained by chi-q over the 2 adic integers and the cycles of H. Corollary 1 is the black sheep of the lot, and it's going to be the Bohm-Sontachi style expression for H's periodic points. So, here's the correspondence principle for periodic points, version 1. Part 1. Let big omega be any cycle of TQ in Z that contains at least 2 elements. Then there is an x in omega and an integer n greater than or equal to 1, so that chi-q of b2 of n is equal to x. That is, there is an n such that the infinite series, the limit, defining chi-q of b2 of n converges in zq to x. And this series is obtained by evaluating chi-q of this number using our closed form formula, and then taking the limit q-adically as m goes to infinity. Part 2. Let n be a positive integer. If the number chi, which is a rational number, chi-q of b2 of n, is a 2-adic integer, then chi-q of b2 of n is a periodic point of tq in the 2 adics. Then, if in addition this isn't just a 2-adic integer, but a rational integer, then chi-q will be a periodic point of tq in the rational integers. And so here's the proof. And recall we write h to denote tq. So let omega be a cycle of H in T with two or more elements. Given any periodic point X in omega, there's going to be a string of length number of elements in omega, which such that the composition sequence H bold J fixes X. In particular, since, again, by that argument that if J does not contain at least one 1, we're going to force X to be 0. So this shows that bold J must contain at least one non-zero entry. A moment's thought shows that for any X prime in our cycle other than X, the entries of the string bold I, which fixes X prime, must be a cyclic permutation of the entries of bold J. Here's an example. For the cycle 1, 2 of the shortened 3x plus 1 map, here are our branches, and the composition sequence which sends 1 back to itself, what we do is we first apply H1 and then apply H0 in that order. On the other hand, the composition sequence which sends 2 back to itself applies H0 and then H1. And lo and behold, the strings 0, 1 and 1, 0 are cyclic permutations of one another. In this way, also we'll deal with this detail more thoroughly in just a moment when we talk about how to compute the things for each individual element of omega, but I'm getting ahead of myself. So in this way, note that there must be some X in big omega and some bold J, such that H bold J fixes X, such that the rightmost entry of bold J is non-zero. From this point onward, we're going to fix X in bold J such that this condition happens. And this is very important because it gets us what we want. So once now what we've done with that, the first observation we make is that since X is a fixed point of H bold J, we can apply H bold J to X as many times as we want. And we will always end up back at X. So X is equal to H bold J composed M times applied to X, which is the same thing as H bold J to the wedge M applied to x. So now we just write out the affine linear map in full using the two different ax plus b forms. Gives us the following, and then let's look. Since the rightmost entry of bold J is non-zero, we know that this is going to have a q-adic absolute value less than 1, and so this will die q-adically as m goes to infinity. So this then gives us that x is equal to this limit, which converges q-adically. Now, let n be the integer represented by bold J, and since bold J's rightmost entry is non-zero, bold J is necessarily the shortest string representing n, and moreover, n is non-zero, and its number of bits is the length of bold J. Then, using our observation about what self-concatenation does to n, we have the following. So just like in proof of our previous lemma, x is equal to the limit of chi q of bold J concatenated with itself m times. This limit converges in the q-adic topology. So now here we're going to replace this by the number that it represents, and then we're going to use rising continuity, or the to get let's just do a brief computation. This will be the key step in our proof of 2, and it involves exploring the fact, as I mentioned before, that the branches of H are continuous self-maps of ZQ. No, not Z2, ZQ. So the claim here is this. Let n be any integer greater than or equal to 1, and let bold J be the shortest string representing n. Then, H bold J is a continuous map on the q-adics, and moreover, this q-adic integer is fixed by H bold J. So let's let n and bold J be given. Using chi q's concatenation identity, chi q of bold J concatenated k times is H of bold J concatenated k minus 1 times applied to chi q of bold J. By proposition 22, we know that B2 of n is represented by the string obtained by concatenating infinitely many copies of bold J. And once again, B2 of n mod 2 to the k is what we get when we concatenate bold J with itself k times. Once again, we use rising continuity. So here, watch where everything goes. We take the limit as k approaches infinity in this equality. This is equal to, we then rewrite this using the definition of chi q and the fact that n is represented by bold J. And then we use rising continuity and this formula to rewrite this as that, and then passing to the limit as k approaches infinity, we get this. So now what we would like to write is if we apply H bold J again on the outside, that this is the same thing as taking the limit on the inside, from which we can conclude that the q-adic integer, this thing, is fixed by H bold J. To make this rigorous, we note that since the slopes of our branches are always going to be odd numbers, our individual branches are homeomorphisms of ZQ, and thus, since homeomorphisms composed with one another are once again homeomorphisms, H bold J is going to be a homeomorphism of ZQ for all bold J. And so now we are going to use the continuity of H bold J not just on ZQ but on QQ as follows. H bold J of our integer, this is equal to H bold J of the limit. Since H bold J is q-adically continuous, we can interchange the limit and the application of H bold J, just like we would do in basic analysis. Then we have H bold J applied to chi q of bold J concatenated with itself k minus 1 times. We then use the definition of chi-q to rewrite it like this, and then we use our string concatenation our string formalism that this is going to be the same thing as h of bold J wedge bold J to the k minus 1, which is just h of bold subscript bold J to the k, which is of course chi-q of bold J wedge k, which is what we did earlier. This is going to be chi-q of this, and as k goes to infinity, it becomes equal to that, which is just chi-q of b2 of n. So this proves that this q-adic integer, whatever it is whether or not it's a rational integer, this q-adic integer is going to be fixed by h bold J. So this here, it's worth pointing out. In the beginning of this thing, of part 2, here we're looking at chi-q b2 of n as a 2-adic number. But in this proof, we are treating it as a q-adic number, and the reason we can do so is because by the way its denominator works, its denominator is going to be co-prime to both q and 2, and that's why we can do this. So this proof requires us to look at things not just from the 2-adic perspective, but from the q-adic perspective as well, in order to capture all the information. So we've proven our claim that h bold J fixes chi-q of b2 of n, where n is the integer represented by bold J. So now let's assume the hypotheses of part 2. With suppose that chi-q of b2 of n is a 2-adic integer. Then, letting J be the shortest string representing n, we know that this 2-adic integer is fixed by this map. So again, this relationship, this fixed condition, occurs q-adically. However, because our map is an affine linear map with rational coefficients, the fact that it's fixed in this realm means that it's also fixed in Q. So this is the craziness of this. We go from this, and so we know that h bold J fixes this number. So now since this is true, we can then apply h bold J times. Because this is a q-adic integer, sorry, a 2-adic integer, by our lemma 7, we then know that the correct string to apply, which is h bold J, will send 2-adic integers to 2-adic integers, which makes this a correct value, which means that applying h bold J is the same thing as applying h bold J times. So this thing, whatever it is a periodic point of h in the 2-adics. In particular, if this number isn't just a 2-adic integer, but a rational integer, then every element of the cycle generated by applying the 2-adic extension of h to this thing is an element of z, including chi-q of b2 of n itself, to which we return after applying h length j times. This then proves that chi-q of b2 of n is a periodic point of h in z, and we are done. Now we have the black sheep. So this is the Bohm-Sontachi criterion type formula, and here let omega be not a cycle of TQ, doesn't contain 0. Then viewing omega in ZQ, the intersection of omega with the image of chi-q over the 2-adics is non-empty. Moreover, for every x in B2 of N1 under chi-q intersection with big omega, there is an n such that this holds. In other words, we're refining the previous version of the correspondence principle to not just say that this is going to be an integer, but we give the specific form, and all this follows just by noting that chi-q of b2 of n is equal to this quantity. That's the only difference. It's what we did before, but we just used the functional equation with chi-q of b2. Also, now this is fun. we then get that x will be a positive integer if and only if mq of n is less than 1, and x will be negative if and only if mq of n is bigger than 1. Finally, with all this done, we can state and prove, also, if you then write out these formulas in terms of all of the products and sums of everything, you'll get the Bohm-Sontachi style Diophantine equation. But this is so much prettier, don't you think? So, now we can finally state and prove the most elegant version of the correspondence principle. This version is also of independent interest because it's this version that's going to give us the divergent points correspondence principle as well. So, version 4, the version of the correspondence principle, version 3 is the explicit, awful, write this out messiness version. It can be confined in my dissertation. Version 4 is the following. The set of all non-zero periodic points of TQ in Z is equal to the intersection of Z and chi-q of rational two-adic integers with infinitely many digits. Where here we're going to be viewing chi-q of that thing as a subset of ZQ. Okay, so let X be a non-zero periodic point of H, and let omega be the unique cycle of H in Z, which contains X. So again, this is a cycle, so by version 1 of the correspondence principle, there is going to be some Y in big omega, and some Z in Z2, where Z is of the form B2 of n, such that chi-q of Z is equal to Y. Since Y is in big omega, there is going to be some k such that applying H k times sends Y to X. That k is then going to then correspond to a unique length k string of I, like length string I, such that hi of Y is the same thing as applying H to Y k times. So now let J be the infinite string representing Z. Then Z is infinite length, and then J is of infinite length and contains infinitely many ones. This is because Z is equal to B2 of n for some n bigger than or equal to 1. Yes, so in particular, since Z is equal to B2 of n, the entries of J are periodic. So using chi-q's concatenation identity, X equals H bold I of Y is equal to H bold I of chi-q of Z, which is equal to chi-q of I wedge J. So let X, let cool X denote the two-adic integer represented by I wedge J. Then X is not an element of n0 because it has infinitely many two-adic digits. That's thanks to the fact that J has infinite length. And by the above, we note that chi-q of cool X is equal to less cool X, and hence that less cool X is in Z intersect chi-q of Z2. Finally, since the two-adic digits of Z equals B2 of n are periodic, it must be that Z is a rational number. Remember, I mentioned this, I believe, in episode 1. The rational two-adic integers are precisely those two-adic integers whose sequences of digits are either periodic or eventually periodic. So Z is not in n0 and is in Q. It's not in n0 because it has infinitely many digits, and it's in Q because its digits are eventually periodic. Thus, Z is in Q intersect Z2 prime. And so, indeed, if letting M be the rational integer represented by I, we have that cool X is represented by I wedge J, which represents M plus 2 to the lambda 2 of M times Z. This shows that cool X is in Q intersects Z2 prime, and hence that less cool X is equal to chi-q of cool X, which is an element of Z, intersects chi-q of Q intersects Z2 prime. So the other direction. Suppose x is in z intersect chi q of q intersect z2 prime, where x is equal to chi q of z for some rational q-adic integer with infinitely many digits. As a rational number, which is both a q-adic integer and not an element of n0, the q-adic digits, there's infinitely many of them, the q-adic digits of z are infinite in number and eventually periodic. So this means there are integers m and n with n non-zero such that z can be written as m plus 2 to the lambda 2 of m times b2 of n. This representation is not unique. But the idea here is that m is the digits of m are the initial part that's not necessarily periodic of z's digit sequence, and then the periodic part is this. So let I be the finite string representing m, and let j be the infinite string representing b2 of n. Then z equals I wedge j. So by our lemmas and the concatenation identity, we have the following chain of equalities. X equals chi q of I wedge j, which is hi of chi q of j, which is hi of chi q of b2 of n, which is hi of chi q of n divided by 1 minus m q of n. So now let's set this number to be y. This is going to be a rational number. Claim 1. Y is a q-adic integer. Since y is a rational number, it's a q-adic number. So by way of contradiction, suppose y has a q-adic absolute value greater than 1. But then that means h bold I of y is going to have q-adic absolute value greater than 1. However, h bold I of y is equal to x, and x is a rational integer. And since every rational integer is a q-adic integer, this means that x has q-adic absolute value less than or equal to 1, which contradicts the fact that this is greater than 1. That's impossible. So it must be that y is a q-adic integer. Claim 3. X is equal to what we get when we apply h to y length I times. Once again, by way of contradiction, suppose the equality failed. Then hi of y is equal to x, but x is not equal to h applied to y length I times. This makes x into a wrong value of h with seed y. But then lemma x of 6 tells us that since x is a wrong value, it has to have q-adic absolute value greater than 1, but that's just as impossible as it was in the previous paragraph, over here, so, because we know that x is in fact a q-adic integer because it's a rational integer. So it has to be that x is equal to the image of y under length I applications of h. This proves the claim. Finally, let a bold v be the shortest string representing n, so that bold j, the string representing b2 of n, is obtained by concatenating infinitely many copies of v. Once again, we note that h bold v is a continuous self-map of zq. As such, we have our string of equalities, chi q of b2 of n, is equal to this limit, which converges q-adically. Now we apply h bold v on both sides. H bold v is q-adically continuous, so we can interchange the limit and the function. We then use the definition of chi q to pull in that v here, and then the fact that this is a limit, this plus 1 goes away, and we return to chi q of b2. This then shows that h bold v of y is equal to y. Since y is then a q-adic integer, which is fixed by h bold v, we may apply lemma 7 to conclude that y is a periodic point of h. Lemma 7, recall, is this guy, which says that if we have a q-adic integer which is fixed by some composition sequence, then that q-adic integer is necessarily fixed by h, is necessarily a periodic point of h itself, which is exactly what we get here. Yes. So what we've now shown is that y is a q-adic integer, which is a periodic point of h. Since By claim 3, h iterates y to x. What we're doing now is, so we have that x is a rational integer, which is a periodic point, and y is a rational number, which is a q-adic integer, which is a periodic point. Both of these are periodic points of h itself. By claim 3, h iterates y to x. Since y is a periodic point of h and z2, this forces x and y to belong to the same cycle of h and z2, and forces x to be a periodic point of h as well. And just as h iterates y to x, so too does h iterate x to y, and since x is a rational integer, so too is y, and thus x belongs to a cycle of h. I misspoke there. I said we don't need to we haven't assumed that x is a periodic point. We're trying to show that. So yes, and you can just watch this. So just to go over here, we started by supposing x was in the image and was an integer, but not necessarily a periodic point. We then wrote x like this. We got this rational number y. We showed that x is in the forward orbit of y, and then we showed that y, which is equal to a chi-q of b2 of n by our functional equation, we show that y is fixed by h. So y is a q-adic integer, which is a rational integer, which is fixed by h, then that h bold v, and then that means that y is a periodic point of h in the q-adic integers, which makes x a periodic point of h in the q-adic integers, which makes y in the forward orbit of x and x in the forward orbit of y, and since x is a rational integer, that forces y to be a rational integer as well, and that completes the argument. So and here's a concrete example, just so that you, in case that was all a little bit too much over your head. So to illustrate the CPPP in action, let's consider the cycle 1, 2, 1 of the shortened QX plus 1 map. We apply the even branch second and the odd branch first. Then the string bold j, such that h bold j of 1 equals 1 is 0, 1. The integer n represented by j is 2. So b2 of 2 has the q-adic digit sequence 0, 1, 0, 1, 0, 1, 0, 1, which by the formula for b2 of 2, this is 2 over 1 minus 2 to the bits of 2, which is 2 has 2 digits, so it's 2 over 1 minus 4, which is negative 2 over 3. So chi3 of negative 2/3 is 1. Now, chi3 of 2, well, we use the functional equation, that's 1/2 chi3 of 1, which is, then we use the functional equation again, is chi3, this is the odd equation, and so we get that chi3 of 2 is 1/4, and m3 of 2 is that, and so that's how we got this particular value. Okay, so now the thing I talked about the cyclic permutations, we're going to deal with that now. So what this result shows is that this composition is a periodic point of TQ for any positive integer, which makes this thing an integer. However, just because all of these things will be periodic points when they're integers, that does not mean that every periodic point is going to be of this form. So this is the distinction between the first version of the correspondence principle and the fourth version. In the first version, and by this way, the second version, we're still using the fact that we're applying chi-q to b2. However, in the fourth version, we're no longer applying chi-q to b2, but we're instead considering chi-q over the two adics in general. So, that being the case, and I am getting winded here, so as an example here, this 1 occurs as the value of chi3 at an element of the image of b2. Since 2 is a periodic point, we can by the correspondence principle, we can write 2 as the form chi3 of something. However, that something is not going to be an element of is not going to be of the form b2 of something, and there's a very simple reason why. It's because in this case, the string that we got ended in a 1. So when we concatenate it with itself, we're going to keep that. However, if we have the string 1, 0, that represents the integer 1, and so concatenating it with itself multiple infinite times is going to give us 1, 1, 1, 1, 1, 1, 1, 1, 1, which is not the correct sequence. The correct sequence that we want, that will be plug it into chi3, that will give us what we need. It's going to be the 2-adic integer whose digit sequence is 1, 0, 1, 0, 1, 0, 1, 0, 1, as opposed to 0, 1, 0, 1, 0, 1, 0, 1. So and now we're going to deal with this subtlety. So suppose we found a positive integer, so that z0 equals b2 of n is then sent to a non-zero integer by chi-q, so that chi-q of z0 is a periodic point. Let's call this x0. Then big omega is the forward orbit of x0 under h. Let xk be the kth iterate of x0 under h. We have then that xk is the kth iterate of chi-q of z0 under h. If, for example, chi-q of 0 is odd, so that x1 is equal to h1 of chi-q of z0, the functional equation for chi-q then tells us that x1 is this, which by using the functional equation for chi-q, we can pass the transformation on the outside to a transformation on the inside. In general, then this tells us that x1 is going to be the image of chi-q at this 2-adic integer, and this is necessarily the unique 2-adic integer with this property. So for each xk, we can now construct a zk, and the procedure is like so. Zk plus 1 is twice the zk if xk was even, and is one more than twice zk if xk was odd. Our situation can be readily explained in terms of cyclic permutations, as I mentioned previously. Zk will be obtained from z0 by adding the k rightmost digits of n to the left side of z0. So for example, if n has the 2-adic digit sequence 1, 0, 0, 1, so that z0 is 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, the z's which create the other element of our cycle would be 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, etc., and 0, 0, 1, 1, 0, 0, 1, 1, etc. And the next number in the sequence, z4, will then be equal to z0. Here, z0 and z3 are the images of positive integers under b2. This is because they are generated by the sequences 1, 0, 0, 1 and 0, 0, 1, 1, both of which end in a 1. The generating sequences of z1 and z2, on the other hand, are 1, 1, 0, 0 and 0, 1, 1, 0, which do not end in 1s. And so our identifications of strings with 2-adic integers ignores all of those extra zeros, and so the value of b2 no longer works. In particular, we then see that because chi-q of b2 of n always has unit 2-adic absolute value, the elements of the periodic points that are of this form are going to be the odd integer periodic points. And the even integer periodic points will then not be of this form. Now the cyclic permutation thing I was talking about before, to do it, we need the shift map. It is currently midnight, and I am eating, what is it? My brain is broken. I am eating cinnamon raisin bread. It is very good. So, the q-adic left shift map, theta 2, is the map which takes a q-adic integer and deletes its leftmost digit. This is the same thing as taking z, subtracting z's value mod 2, and dividing by 2. Theta 2 is the quintessential example of an ergodic map on the q-adic integers. Here, ergodicity is with respect to the real valued hard probability measure on C2. So the, the cyclic permutation thing is this. Let big omega be a cycle of t cubed that in the integers that doesn't contain 0. Let n omega be the smallest positive integer so that chi q of b2 of n omega is contained in big omega. Then let big theta big omega be the set of two adic integers we obtain by cyclically permuting the two adic digits of b2 of n big omega. That is, big theta big omega is the image of the forward orbit of b2 of n big omega under the shift map. Then for z in z2, chi q of z is going to be an element of big omega if and only if z is an element of big theta big omega. In particular, the restriction of chi q, this set, is a bijection from the big theta big omega onto big omega, and the number of elements in big omega, the number of elements in big theta, is equal to lambda 2. This should be an n omega, my bad. This should be an n omega.